Thanks, Bernd. So welcome everyone to session 4 of the PML School. And so as Bernd alluded to, on the formal agenda at the start of the series, we had scheduled nonlinear kinetics. And during each of these sessions, we get lots of feedback in the form of Q&A questions. And so far, we've been using primarily the built-in and the textual models in the Phoenix model object. And many of you have been asking about how to edit Phoenix models in graphical mode. So for this presentation, we picked a topic that lends itself well to graphical models so that we can introduce this way of editing models. And this will be PK43, multiple absorption routes. So for the exercise here, the background, the protocol was that one subject received a 2 milligram sublingual dose of a new analgesic compound, X. This compound is absorbed rapidly via the buccal route, with also a delayed absorption that occurs in the gastrointestinal tract. Following the dose administration, plasma concentration samples were collected. And it is known that compound X has a one-compartment elimination. So what's the objective? The objective is to characterize the absorption of the analgesic by both the buccal and GI routes with a different rate of absorption, Ka, for each, model one-compartment elimination, and then find estimates for the following PK parameters. Ka1 is the rapid absorption in the buccal cavity. Ka2 is delayed absorption rate via the GI tract. V is the volume of distribution. K is the elimination rate. And then F rapid is the fraction absorbed via the rapid buccal route. And 1 minus F rapid is the remaining fraction absorbed via the GI route. And then lastly, there's a lag time on the absorption via the GI route, and that's parameterized as T lag. Okay, so we will begin the exercise with exploratory data analysis, plotting the data to see the profile. As you can see here, we have multiple absorption phases here. So then the question becomes, how do we model something like this? So we're basically going to break this up, the administered dose, into 2 phases, each of which has a fraction in order to model this appropriately. So if we look at the built-in model options in the Phoenix model object, there is the option to add a T-lag. So we have here a PK model type with a microparameterization, extravascular absorption in one compartment. We can certainly add a T-lag, but that is not sufficient in this case to model the entire absorption profile, since there's 2 phases to it. So the solution in this case is to use one of the graphical model options. So the graphical model in the Phoenix model object, you access this by clicking Edit as Graphical, and then you can edit the model in a graphical form. You have a toolbar palette that you can add different compartments and different aspects to the model. So in this case, we see that this is the central compartment, the blood plasma, which has a volume of distribution, an amount, and then the concentration is the amount divided by the volume, and one can take samples here with this green observation block. Then, to model the dose input into the central compartment, we break it up into these 2 absorption routes. So here we have the buccal absorption with a rate of Ka1, as well as the delayed absorption via the GI tract with a Ka2. From the central compartment, there is a one-compartment elimination parameterized as Ke. And we also have some additional structural parameters. That's the fraction, F rapid, which is going to be for the buccal route, and then 1 minus F rapid will be to parameterize the GI tract. And then lastly, we have a T lag, which is applied to the GI absorption. Okay. This type of model can also be expressed via PML code. This will be presented during the demo portion, But if you actually look at the PML code, there are numerous entries you put in for the dose point. So just depending on how you like to edit the model, you could certainly write it this way. But it might be easier for some of us to think of this in the graphical mode. Okay. For PK43, the initial estimates for the model will be the rate of elimination, which is obtained from the NCA terminal phase regression, the volume of distribution obtained from NCA analysis, the absorption rates Ka1 and Ka2 can be obtained graphically, the slope of the first pass ascending limb and of the second pass ascending limb respectively. And then the fraction absorbed via the rapid buccal route can be obtained from NCA. So if one were to calculate the AUC following the buccal route divided by the total AUC for the entire profile, one can get an initial estimate for the F rapid. And then lastly, T-lag is straightforward to obtain graphically. It's simply the start of the second pass absorption. Okay. So at this point, what I would like to do is switch over to my Phoenix application. And I'll pause here for a moment and see if anyone has any difficulty seeing. But I am now in the Phoenix application.
Looks good, Chris.
Thank you. Okay, so here we have the input data. And with the input data here, we have times and plasma concentrations expressed in micrograms per liter. Okay. And here we have the exploratory XY plot, where we can see both absorption phases displayed. This is on a semi-log scale. And in the terminal phase, we see that there is a one-compartment elimination. Okay. So I can certainly start thinking about doing a Phoenix model here. So I can go ahead and send the input data to Phoenix modeling and then Phoenix model. And I'll start building the model in the built-in mode. So we'll use the microparameterization with an extravascular absorption. So I could check this T-lag option, and that would be if there was one dosing input. However, since we have two different routes of input here, we're actually going to customize this. So I'm going to leave that unchecked for the time being. I will want to map the time variable as well as the plasma concentration as C-obs. Next, we'll go ahead and enter the dosing underneath the setup panel. And so the amount here, 2 milligrams, we do recommend entering the dose with the same mass units as the mass portion of the concentration. So since the concentrations were in micrograms per liter, the dose will be entered as 2,000 micrograms. And then the time of administration is time 0 relative to the profile. Okay. Okay. Next, I will go to the look at the model, and I'm in built-in mode at the moment. So if I want to create this as a graphical model, I'll go ahead and click on the Edit as Graphical option and select Yes. And then go ahead and start constructing the model. So we have a one compartment, a central compartment with elimination. So the elimination portion is okay right as it is. But I want to be able to customize the inputs here. So what I'm going to do first is I'm going to call this the buccal. Okay. And give it a bioavailability, and I'm going to call this F rapid. Okay. And then the rate of input is going to be Ka1. And depending on how you like to look at these, you can also change the sizes and change the positions of these. So it's one of the nice features of the graphical model editor. Okay. At this point, you also have a toolbar palette where you can add different compartments: absorption, central, elimination, peripheral, PK flows, observations, and so on. At this point, what I want to do is add an absorption compartment. I'm going to add this here, and I'm going to call the second absorption compartment GI tract. Okay. And from here, I can add a PK flow. So I'm going to click on the PK flow, click on the GI tract, and then click on the central compartment to connect it. Okay. So now I can reposition my absorptions accordingly. And then for the second input, this will be expressed as Ka2. Some additional aspects of the GI tract are that I want to have a T-lag. Okay, so I'll parameterize this as T-lag. And then the bioavailability will be 1 minus F rapid. Okay. Now, I've added some custom parameter names here. These are the T-lag and the F rapid. So I will need to add these as structural parameters. I'm going to right-click and then select Insert Parameter. And the first one will be T-lag. And then I can insert a second parameter, and we'll call this F rapid. One thing to be mindful of when using this graphical mode or PML is that it is case sensitive. So this capital F is important, and then the lowercase, the rest of the parameter name. Okay. So at this point, I've built my model. And then the next step is to do the initial estimates. So I've clicked on the initial estimate, and remember that this is the graphical representation. You see the observed concentrations represented by the circles in the panel on the right side. We'll start with time. Okay, and then I need to put in some initial estimates for these parameters. And how does one determine these? Well, one handy tool to do that is the NCA model object. So I'd like to briefly go through and show how to derive some of these initial parameter estimates that we will ultimately put in as our initial values. Okay. So I'm going to take the input data set and first get the elimination phase, and I can do that with the entire profile here. So what I'll do is right-click the input data set, and I think I'll go ahead and put in a sub-workflow called initial estimates. So we'll call this initial estimates. So from the input data set, we'll go ahead and send this to NCA in Toolbox, and then NCA, and then put it in my initial estimate sub-workflow. Okay. And so I will make some selections here to set up a non-compartmental analysis. Okay. So the dose amount is 2,000 at time 0. We have an extravascular administration. The dose amount is microgram. Set the calculation method to linear up, log down. And NCA has a default algorithm for determining the terminal elimination phase, so I'll just simply go ahead and execute the NCA at this point. And if I look at my final parameters, I'm able to get parameters such as the AUC last, AUC and spread, and the lambda z, which is the estimate of the elimination rate. We have this here at 0.085. Okay. Now, if I go back to the exploratory data, if I want to characterize the fraction, if I want to break this up into fractions, what I can do is do an area, an AUC infinity for the first portion, the first phase, and also an AUC infinity for the second phase. and do the ratio. So basically the AUC of the first phase divided by the total AUC infinity will give me an estimate of the fraction in the rapid phase. Okay, so in order to set that up, I'm going to use a data wizard. And I'll need to identify the phases. So if we go back to the XY plot, if I rest my mouse on this, this actual observation here, I get the coordinate value. So it's at hour 2, the concentration is 42.1. So my estimate for the end of the first phase and beginning of the second phase is at 2 hours. So what I want to do is go ahead and take the input data set and then send it to the data wizard. And I'll put this in my initial estimate sub-workflow. And at this point, I want to isolate just the data that's before 2 hours. So I'll click, do a filter operation, then click Add. And I can use a built-in filter with the action Exclude. And I'll find the value 2 in the time column and exclude values that are greater than 2. Okay. So I can click OK and then execute. And so now my result is a data set that just has concentrations from dosing time to 2 hours. And then I'll take this result from the data wizard and send this to another NCA object. And I'll call this NCA time less than 2. Okay. Okay, and enter in the administered dose, which is again 2,000 at time 0. Dose in microgram. And we'll go ahead and run the NCA model. Okay. So I have here the NCA just for the first phase. And the objective of this, again, is to get the AUC values. Okay. Okay. So at this point, I want to get a good estimate of the F-rapid. So I'm going to use some data tools here. I'm going to start with the entire profile and take the final parameters pivoted and send it to another data tool called the append worksheets. Okay, and I want to pull in the subject column, and I'm going to use AUC and spread from the entire profile. Okay? And with the append worksheet, we have 2 worksheets, worksheet 1 and worksheet 2. So the first worksheet is from the NCA from the entire profile. Worksheet 2 will be the NCA from the time less than 2. And I'll take its final parameters pivoted worksheet. Again, mapping both subject and AUC and spread as source columns. And then I now have a combined worksheet where I have the AUC and spread for the entire profile and then for the first phase. Okay. I will use one more data tool to pivot these and put these into 2 separate columns. I'll go ahead and send this to data and then pivot worksheet, where the column header is my source, the values are the AUC and spread, and then the row header is the subject ID. And I'll go ahead and execute. So I now have the 2 values next to each other, and there's a data tool here where you can do a transformation to perform the simple operation of dividing this value by this value to get the fraction. So I'll send this to data and then data wizard. The action in this case is transformation. This is something that you can use to divide the contents of one column by the contents of another column. And we can do a simple arithmetic transformation, which is x divided by y. And this new column name, we'll call this F rapid. Okay, and then I just need to identify the X column and the Y column. So the X column is NCA for the time less than 2, and the Y column is the NCA for all times. And then I can execute. Okay. So my estimate for F rapid is 0.55. Okay. So now I have an idea of some of my initial estimates. So the purpose of this, again, to determine initial estimates. So I'll come back to my graphical model. Generally, it's probably a good idea to use naming, so I'll call this the graphical model. And go to the Initial Estimates tab. Okay, so for the initial estimates, I can see the observed circles here. In order to see a predicted line, I have to enter in dosing. And notice that since I have defined these doses, I'm actually going to enter the same amount for both the buccal and the GI tract. And then the fact that we are dividing these into fractions is going to split up the dose into both of these. Okay. So initial estimates, the volume of distribution, I can get that from the NCA. So I want to click on the NCA for all times, and then find the volume of distribution. So that will be here. That's 21. I can come back into my graphical model. And my volume of distribution, I'll go ahead and type in 21 as my estimate. The KE is going to be the lambda Z from the NCA. So I can go ahead and find this lambda Z. It's about 0.085. Okay. I'll round that to 0.9. So we already see that, that the predicted line is starting to behave according to these parameter estimates. The T lag we can observe from the graph is going to be 2. The F rapid from the data wizard was about 0.5. And then we have the two fractions. These can be determined graphically from the first pass and the second pass. Okay. And so here we have some initial estimates.
Chris, can you change the KE to 0.09?
Oh, thank you. Thank you, Bernd. Yes, I was off by an order of magnitude there. And then we're starting to get close to the profile. Okay. And we can also look at this on a log scale. So these are pretty close for the initial estimates. If I check these boxes here, this ensures that these are all positive, so we do not have negative values for the initial estimates. And we'll go ahead and copy these to the initial estimates. And at this point, we're ready to run the model. Okay. So I can look at my final parameters, which are going to be on the theta worksheet. And we also get the fitted curve, which is represented here. Okay. So these were the final parameters where we have the estimate, the standard error, and the coefficient of variation for the parameter. If I then want to look at the model in a textual mode, just to see what the PML looks like, remember that no matter what interface you use to edit your model, whether it be graphical or built-in, the underlying code is all written for you in PML. So at this point, what we'll see is how is this represented in the graphical mode. I can simply copy my Phoenix model object and then paste it back into the workflow. And I will call this my textual model, where in this case, I switch over to edit as textual and say yes to edit the model as textual. And then under the setup panel, I go to model, and I'll comment on some of these sections here. So the differential equation for this is for the amount function. So the amount in the central compartment is A1, and here we have the elimination plus the absorption via the buccal route and the absorption via the GI tract. The urine compartment is used for elimination. And we also have the change in the buccal as well as the GI tract. And then the concentrations are obtained from the amount in the central compartment divided by the volume of the central compartment. And some of the inputs in the PML code, we use the dose point statements. So for the buccal, that's defined with a bioavailability set to F rapid. The dose variable is buccal dose. And then this inf dose variable, that's in case the dose is an infusion. In this case, it doesn't apply, so we simply left the inputs for this blank. And then the infusion rate variable, buccal inf rate. So that's constructed for us, but we actually don't need those in this case, so we just simply leave them blank. Here we have the error, and as well as the observed statement. So this is an additive error model. So we leave this to its default, which is C obs equals C plus C epsilon. And then a similar dose point statement is made for the GI tract, where the T lag is added. So that's something that the buccal route did not have. Bioavailability is 1 minus F rapid, and then the rest of the dose point statement. And then by default, we do get these parameters declared as structural parameters. So the volume equals typical value for volume, KE, KAs, T-lag, and F-rapid, and so on. And then lastly, the initial estimates are entered in the fixed effect statement, and then these were just simply copied over from the previous model object. And so one can actually just go ahead and run this in the textual mode. It has all of the inputs since I copied the model. Okay. Here it took to the residual plot, but we should get the same outputs from the textual mode that we did in the graphical mode. Okay. So this concludes the planned demonstration. Do we have any questions at this point?
Okay, yeah. Okay, so we are starting with collecting questions. So there's a Q&A panel on the right-hand side of the console. So I would ask, if you've got some questions, please post them there, and we can respond to some of those maybe in the live session. And as we usually do it, we publish the questions together with the answers on our forum. So that we have a couple of questions coming in. Chris, there's one: how do you choose the error model? This is a very typical question. Yeah. So how do we choose the error model? And that's typically so first, what one does is fit the structural model, and then if you have if you think you have a good model based on the diagnostics and the objective function, particularly if you have more than one profile, you can further refine the model with an error model.
I'd actually like to, I believe Dan Weiner is on the call, and I'd like to invite Dan to comment further on the selection of error models.
Sure, I'd be happy to. Are you able to hear me okay?
Yes.
Yeah.
Yeah. So basically, with regards to the error models, one would do an analysis of the residual plots. So if we go to the results section, here we've started with an iterative model. But if you look, for example, let's look at the, residual versus I-bar plot. This looks, I like to use the word a little gnarly. It's not as ideal as you'd like. Ideally, you'd like the red lines to be parallel and the blue line tracking 0. But in situations like this, where it's very, what I call poor resolution data, you have very, very few data points. You often get irregular patterns like this. And in this particular instance, where you see the red lines converge together, but there's no data really associated with that range of the data. So I don't worry about that one, that particular aspect of the profile so much. And then if we go to the other residual plot, which is 2 above, Chris, where we look at weighted residual versus spread, we see the same sort of situation there, but here the blue line's tracking 0 pretty well, and the red lines are fairly parallel. We've got a little bit of curvature, but as I said, that's not all that unexpected in situations where you have small numbers of data points. And then lastly, I looked at the QQ plot, which is the last plot. And here you're looking to see, you're looking at the quantile plot of the observed residuals versus a standard normal distribution. And if the residuals are fairly normally distributed, they should fall very close to the line. And that's pretty well represented here. So in this case, the residuals would look pretty good. If you saw a bend away from the line, either at the left-hand side or the right-hand side, that generally would be indicative of the need for some sort of residual error model to be employed. And if you saw deviations from this line that were more in the central part of the curve, that could be weighting, but that's generally more indicative of a structural problem with the model. So you might want to try adding additional compartments or possibly looking at nonlinear kinetics. So I'll pause there, Chris.
Okay, yeah, thanks, Dan. Maybe we jump to the next session. A question. Here's a question about why linear up and log down was used as a calculation method for NCA.
Mm-hmm. Yeah, so I'll go ahead and field that one. And so remember the initial profile here. And so if we're looking at this, we actually have multiple absorption phases. And so the elimination phase is typically fit with a log linear regression, whereas the absorption phase might be fit with a linear. So when you choose the linear up log down method in the non-compartmental area calculations, it uses the linear trapezoidal rule when the concentrations are increasing, and it uses the log trapezoidal rule when the concentrations are decreasing. And since we had these multiple peaks in the profile, this is the reason the linear up log down was selected.
Okay, there's a question here. Can unique initial estimates be input for multiple individuals using the graphics model?
Yeah, so when you go to the initial estimates tab, it's asking for one set of estimates. You can certainly sort by multiple subjects, and we've actually seen this in some of our other presentations where we had multiple profiles and you get an overlay. In this particular example, we only have the one profile. But when you enter in the initial estimates, you can actually see an overlay of all of the subjects and then apply the initial estimates accordingly. If you sort by the subject, the actual fitting will then resolve those initial estimates into individual PK parameter estimates by the model fitting. But to answer the question specifically, it's asking for one set of parameter estimates for the overall model.
Okay.
Yeah, so Chris, before he goes ahead, Chris, you might want to mention, if it had been a sort key, how one would have assigned different initial estimates for the different subjects. I think maybe that was the question.
Okay. Yeah, so what you could do is, if you go under this setup panel, there's an additional parameters input here that you can use. You can use an internal worksheet, and in this case, you can go subject by subject. So in this input, we only have the one subject here, but if there were multiple subjects, you could actually put in initial values, and then this spreadsheet would continue to accept initial estimates for the other subject.
Okay, good. Let's go to the next question. Where are the iDose var parameters set if you would need them, if you want to apply them for your model?
Yeah, so so in the textual model, this is done using these statements here. So if you want to use the textual mode, each of these components, they're comma delimited, and if you wanted to enter this, you would set this under the dosing setup. It accepts the possibility of an infusion dose. If you go ahead and rebuild the dosing under setup dosing, were this an infusion dose, you could put in the buccal rate and the GI tract rate, which corresponds to those input doses. And again, that's predefined with this equal statement defining the variable name.
Okay. Yep. Next question, can you just repeat again the part where you determine the initial estimates for the absorption rate constant?
Mm-hmm. Yeah, so these are typically determined graphically. So for the absorption rate constant, you could simply get the slope and intercept by regression of the absorption phases. In this case, what I did was I used the graphical model. Since we had this built in, I had entered values for the volume of distribution, the KE, the T lag, and F rapid, and I was able to visualize them here. You can certainly use data tools and do basically a regression of the two absorption phases separately, but I found it convenient to use the tools that are available here. So you can see as I increase the KA2, for example, the second limb starts to increase. Okay.
Mm-hmm.
So taking advantage of this nice feature of Phoenix models.
All right. Another question, can we model discontinuous absorption in Phoenix, and can we build transit compartments in the absorption phase? Yes,
both of those are possible. So you can use some special statements called sequence and sweep statements to turn inputs on and off. And you can also model transit compartments. There's a transit statement that allows you to parameterize a transit compartment. This is possibly something we could consider for a future exercise if desired.
There's one question here asking about, is it possible to have covariate effects on Ka for multiple dose sites?
Yeah, any of these structural parameters can have covariate effects assigned to them. That's when you run in the population mode.
And maybe the final question for this round. When and how to select lower and upper initial estimates, the boundaries for the initial estimates? Sure.
Yeah, that's a good question. So let's have a look at this parameters tab, fixed effects subtab. So sometimes if you have a difficulty fitting, you might do an initial run and get values that don't make sense somehow. Either there's some sort of problem with the model, so you can confine the parameter space by defining lower and upper boundaries. So for example, a logical lower bound for any parameter really in the physiological realm is going to be 0. So these are all going to be positive. You know, we wouldn't have a negative volume, for example. And then our rate, so lower bounds are all positive. And then if you want to somehow constrain, you might say that the volume of distribution should not exceed 1,000 because it would be nonsensical. Or you might want to constrain the rate to no greater than 2. It really depends on the system that you're studying. And the nice part about Phoenix, it's very flexible. You can put bounds on only one parameter. You can put bounds on all parameters. If you're highly confident in one of the estimates, for example, this T-lag, you can even freeze the parameter. You can say, look, we looked at the data and we know that the second phase started at 2 hours, so let's fit these other parameters, and sometimes that can help with your model fitting.
Chris, this is Dan. Could I just expand on that just a little bit?
Sure, please do.
Sure. Everything Chris said is absolutely true, but there is some other commentary just based on the actual optimization algorithms. All of these algorithms, they like to work in an unbounded space. So they don't, you can think of it as they don't like bounds in general. So ideally, you should try to get good initial estimates, and Chris did an excellent job discussing how to get these for this model. And I would first try the model fitting without boundaries. If you have some difficulty then, whereas Chris said the final estimate is outside the range that you would expect, then the next thing I would try is to put a boundary, but only a lower or upper. Do it unidirectional and see if that gets you in the right space. And if yes, you're done. If not, only then would I give both a lower and upper bound. And again, this is because of the nature of how the algorithms are written. They do perform better in an unbounded space.
All right. Yeah. Thanks, Dan. Thanks, Chris. I think we do stop here with the Q&A session. And as usual, you will get an email message from me where I point you to the topic in our forum where I upload all the materials. So what we do there, we put the slide deck that Chris presented to the forum, the textual model, and the link to the recorded webinar. And as soon as we are done with finding, phrasing responses to all your questions, so all those questions that you sent to us, posted to us, we will answer those and will also post them on the forum, and I will notify you where to look up those. So thanks everyone for your interest. We have the next session in 2 weeks' time. With also a changed topic in this case. So we are looking at plasma and urine kinetics. And with this, I would like to close this session, so you may disconnect now. Thank you.